150 does not mean anything. The point is, among all the potential trees we have calculated, these are some of the lowest scoring nodes. The lower the score, the better the tree is, the less impacted it is by wind failures. So you can see two variants here with a, in our scenario, quite good impact score, which are valuable to valuable. And as written here, we can minimize this metrics or minimize these results, and then we find the best possible trees in that sense. Metrics. Here we again have two potential approaches. So we could look at the distance between the grandmasters and the network nodes, so the distance calculations, and we could look at the order, which is an evaluation of the quality of the clocks on that. But again, with doing simulations and calculations here, we found out that the order case is sometimes leading to unexpected, not best results, and that's why we substitute the distance calculation, where we basically say the shorter the distance of all nodes to the time provider, which in general or on average in the network, the better theoretically your position is. I mean, with every block you have theoretically some little additional, I would say, impurity or variance in your time synchronization. That's why we continue on with the distance calculation for that. So again, the same network and the same grandmasters, we did distance calculation and have again some values which are in our case lowest values which we found out, having a distance of 67 from the left hand side tree, having a distance of 63 from the right hand side tree, and as before with the impact score, the absolute number does not really mean anything. It's just that this is these are the lowest scoring numbers in all the possibilities which we evaluated. So to show you how it would look like in a plotted manner, basically we have an X and Y axis, with the X-axis denoting the robustness score, and as already said, the lower the score, the better. And the Y-axis denoting the precision score, again, lower value meaning better. So obviously, in the ideal case, you would look for something which scores in the bottom left part of your diagram here, which in our case was not really the case. So we have quite some distribution here, and this distribution over all possible combinations you look at could theoretically look completely different for other scenarios or networks. But simply put, you want to have something which is on the lower left-hand side. And in the figure, just to note, the worst precision score is assigned. So we look at both spanning trees for every grandmaster, because we said we have two domains for every grandmaster, and the lower precision score we take to denote here. So what you can see now here is we now showed, for example, trees in a way that the left-hand side, this is a precise tree set of two spanning trees for that GM, and on the right-hand side you see that's a robust spanning tree set for that GM. Meaning, on the left-hand side you potentially have lesser hops or lesser number of jumps in your overall spanning tree. On the right-hand side, you are less prone to impact of a wind failure. So we decided that the more important thing to look at, and that's why we built up our process such that we start with a robustness. We decided that having a robust spanning tree is more important than having a precise spanning tree. So we decided to look at the most robust combinations first, and we will use the robust combinations then to already lower the number of potential spanning trees to look at, and then we use those to look at the precise ones, and then we only separate the types. So if we have a robustness score which is similar for a couple of trees when we try to resolve those ties by looking at the precision metric score. So basically, what we initially said, with these two metrics, it is therefore possible to find the most precise of most robust spanning trees on Grandmaster. So now don't get confused. I'm skipping briefly over the multiple time decision checker, but we'll come back to that. So for the Grandmaster synergy, let's look at this case here with a simplified network setup now with a Grandmaster on the top and different potential spanning trees for its two domains. So now we are adding a backup or secondary hot standby Grandmaster to the right here, each time, again with different spanning trees. And the point now being, it's sort of an academic problem, but in case you would have two link failures at the same time, you can have the situation that, depending on how you set up your synchronization trees, either you have a good spanning tree in some sense, that even with two link failures, you are lucky that one of your domains still serves everything in your network. So here you can still have a time synchronization within all your nodes, which, as you can see, is not the case on the right-hand side. So this is just with different spanning trees, but with the same GM and backup GM. And here, if you are unlucky and have a bad or not the correct spanning tree selected, then you can be in a pity because you can see that the spanning trees are not propagating anymore, meaning parts of the network is disconnected from the time synchronization. And to find that out and to ensure that we get something like that and not something like that, we do the impact calculation as shown before for all. It's a little complicated combination of three failures, or I should say n minus 1 failures depending on the number of domains which you look at. So we have 4 domains in total with 2 Grandmasters, meaning we look at 3 failures. And the least impact score we get is are the trees which we should look at. And now, as I said, don't get confused. Now, we're stepping back once because this is one of the key points we want to emphasize here is this multiple time-based issue checker. So, what's behind that term? I mean, as before, similar network, but now, don't get confused. Primary GM still on top, constant by GM on the bottom. Constant by GM meaning it gets fed both domains from the primary GM, synchronizes itself and sends the synchronized time back out as its own 2 domains. Now we can have a strange issue. So again, let's assume we have 2 link failures, this time here in the middle and to the right. And here what we have now is that if you look closely, you see that part of a network is being served by the primary Grandmaster time. Part of the network is served by the backup Grandmaster time. So the primary served nodes in the network are the ones which have a solid cursor around them, and the backup served nodes are the ones with a dashed cursor around them. So in this case, we have a very special circumstance where it can lead to quite hard to detect issues and debug issues, we guess. Then the hot standby GM is still working. Of course, it doesn't get synchronized to the primary GM anymore, but it still serves time. And now we have parts in the network which look at this time, which can drift obviously, and we have parts of the network using another time. And if you now employ something which is time sensitive, like the task traffic checker, for example, then you can have the issue that both nodes, which would need to communicate with each other, can have different understandings of time, drift apart, and then you can run into all sorts of hard to debug and detect issues if this time is slightly off from that time regarding gate states, whether they are close or not. So with that, we thought that there must be some solutions how to circumvent that. So one solution obviously is don't rely on the primary time being sent to the hot standby GM, but use a redundant GPS webmaster. With the drawbacks we saw initially, they can drift, they can have different time bases on their own initially, it's additional cost, etc. You could use a very good clock in the hot standby grandmaster, or a very good precise oscillator crystal that is good enough that it can work within given limits until the mission is finished. I mean, a car usually would not run for more than, let's say, 24 hours. And if your drift is little enough, then maybe that's good enough. Or you can ensure that the hot standby GM cannot possibly be disconnected from the primary GM, time synchronization-wise, such that the network is split in two. And that's what we looked at. So our solution here is to add domains to cover all possible paths between the two GMs. And in our example, just come back for a second, in our example, if we would have another domain in the primary grandmaster taking the left path downwards, then we wouldn't have the issue. Then the hot standby GM would still be synchronized to the primary GM. Of course, that's very simplified, but finding that sort of solution in a more complex network can be quite a task. But that's, as I said, what we proposed here, and that's why we have this feedback loop as I have shown before. So now closing that out with sort of a demonstration where we try to go through all of the chain. So we have the same bigger network which we have shown initially. We have predetermined that we have the primary grandmaster sitting there and the backup grandmaster sitting there. And as also already done in that for our presentation, we have two domains of grandmaster. So we look at the spanning trees and the possible ones which we can use with those grandmaster placements. So per grandmaster we come up with 12 spanning trees, which we have to evaluate. For each grandmaster, then we look at the robustness values for those two spanning tree sets. In total, practically this yields 66 combinations. Out of that, we take the first example, meaning the first equal ones with the lowest same score for continuation in our algorithm. This, in our example, led to 6 two-spanning tree sets for the primary grandmaster and 4 two-spanning tree sets for the backup grandmaster. We then feed that into the multiple time transition checker, where, as we said, come up with a solution. In our scenario, we only have to have one domain if we want to be safe from that split time-based time understanding issue which we showed. So here is where you can basically feedback, add another domain for resilience, and then have to do the robustness again. But in this case, we continued with the 6 to 4 set of two spanning trees. Combining those or looking at those possible combinations, we have 24 possible combinations. And with the metrics or the impact methods we have shown before, we number that, or we reduce that number down to 8 exact combinations again. And in the precision metrics, we do this evaluation for the remaining 8 combinations. And this then, in our case, that's only one combination showing the absolute lowest value. So what you can see down here, this and that is that combination of the most precise spanning trees among all 4,356 possible configurations. So this is it's sort of a brute force approach, but with that you can really get your most precise tree, your most robust tree. So this is the method for getting those. As said, it's a brute approach, but we would say it's a reasonable execution time. So in our example, ran on the primary standard desktop PC, normal, powerful. We ran it with 2 minutes and 30 for 2 GMs and 2 domains. And then we looked at 3 domains to be resilient to this disconnection errors. It went up to around 5 minutes. But keep in mind, this is not something which needs to be done in vehicle operation. This is something you do once when you design a network. You design the next IDN, And then you can run this approach which we proposed and get the best possible set of spending trees and the spending tree configuration and placement out of all the possibilities you can think of. And what's also very interesting is the same metric can theoretically be used to optimize even the placement of the grandmasters themselves. As I said, we have predetermined that primary grandmaster is there, secondary grandmaster is there. I mean, sometimes it's just physically that the OEM says it needs to be the antenna module, so this will be the primary. But maybe the secondary can be placed wherever we want to, and we want to find out the best possible placement. So you could run that with enough time for every single possible combination. And then you would even get the best placement in the whole network for the primary and the secondary grandmasters. So, with that, I'm done. I hope I was able to somehow convey parts of the study. As said, this is part of the PhD thesis of our colleague Quentin. His PhD thesis is available publicly if you want to dig deeper. Feel free to reach out to me. I can also get you in contact with him. But until then, I'm free to answer any questions, hopefully, which might come up before lunch. Thank you.
Thank you. We have time for a few questions for Daniel, recognizing he is standing between you and lunch. So no one's getting right up to asking questions. All right. Well, with lunch on the way, I won't push it. You know where to find Daniel year-round. Just a quick announcement. Lunch will be served downstairs off the lobby. It's called the Windsor Room, so it's right off the elevators. There's also a staircase if you want to not have to wait for the elevators, which is right next to them. Lunch will be 90 minutes. You can also feel free to visit the exhibitors during that time as well. And you're going to reconvene with talks starting at 2 p.m. So thank you. Enjoy your lunch.